Long before equations existed, humans noticed something fundamental. The world could be counted. Counting transformed physical things into something abstract, numbers that existed regardless of what was being counted.
Some quantities can be divided into smaller equal groups, without anything being left behind.
But other numbers resist every smaller equal grouping. Something always remains, or the number stays whole. These are prime numbers, whole numbers greater than 1, divisible only by 1 and themselves. They become less frequent as numbers grow, yet no matter how far we count, prime numbers continue.
But their spacing is irregular. Sometimes primes appear close together. Elsewhere, increasingly long stretches contain none.
They are not random. Their distribution follows deep mathematical laws, but never settles into a simple repeating pattern. Every whole number greater than 1 can be built uniquely from primes, making them arithmetic's fundamental building blocks.
More than 2,000 years ago, Greek mathematicians proved something extraordinary. There can never be a final prime.
Individually unpredictable, yet collectively structured, primes reveal a recurring mathematical theme. Irregularity can still contain order. Numbers revealed hidden structure. But when humanity turned from counting to shape, another mystery was waiting. From counting, humanity turned to shape, and encountered one form whose hidden ratio would appear again and again. Make a circle tiny or enormous. One relationship between its width and its boundary never changes. Measure straight across the center of any circle. That distance has a simple name: its diameter.
Now measure once around its outer edge. That longer distance is the circle's circumference.
Divide circumference by diameter, and every perfect circle gives exactly the same constant.
We call that constant pi, approximately 3.14, with digits continuing forever without repeating.
Civilizations measured circles for thousands of years, gradually discovering that this stubborn ratio never changed.
But pi did not remain trapped inside circles. Rotation connects it naturally to oscillation and waves. Whenever systems repeat through cycles, the mathematics of circles can reappear, even when no circle is visible. A swinging pendulum seems far removed from geometry, yet its idealized timing equations can contain pi. Across geometry, probability, and physics, pi keeps returning, because circular and periodic structures appear throughout mathematics. The circle gave us pi, but an even simpler shape, the square, would expose an entirely different kind of number. A square seems almost too simple to hide a mystery. 4 equal sides, 4 perfect right angles. Imagine each side measures exactly 1 unit. Every length around the square is perfectly rational and familiar. Now connect one corner to its opposite. How long is that single diagonal line? The Pythagorean relationship gives the answer. The diagonal squared equals 1 squared plus 1 squared.
So the diagonal is the square root of 2, approximately 1.414213.
Perhaps it was simply a fraction. Mathematicians searched for 2 whole numbers whose ratio matched the diagonal exactly. fractions could approach it astonishingly closely. But no ratio of two whole numbers could equal it exactly. Irrational does not mean chaotic. It means the number cannot be written exactly as a fraction of integers. Its decimal expansion never terminates, and never repeats in a fixed recurring pattern. The number may resist every exact fraction, yet its length exists perfectly between two corners of a square. Whole numbers and fractions were not enough. Between them lay an entire continuum of numbers the mathematics had to embrace. Geometry revealed numbers beyond fractions. Next, a simple numerical rule will lead us from mathematics into living growth. 1, 2, 3, 5, 8, 13. At first, it looks like just another sequence, a simple pattern of growth. Its rule is remarkably simple. Each new number is created by adding the two immediately before it. Living things do not solve equations. They grow, one new structure emerging from what already exists. For a plant, each new leaf competes for light and space with everything that grew before it.
Botanists call the arrangement of leaves around a stem phyllotaxis. And some arrangements reveal striking numerical regularities.
Look closely at a sunflower head. Thousands of developing florets packed together in two opposing families of spirals.
Similar counts appear in pine cones and other plants, where new structures must repeatedly fit into limited space.
Count those spiral families, and their totals often land on neighboring Fibonacci numbers. Repeated growth at changing angles, efficient packing, and Fibonacci relationships can emerge from that process. But nature is not a Fibonacci machine. Not every flower, shell, spiral, or branch follows this sequence. Now divide each Fibonacci number by the one before it. As the sequence grows, the ratios approach one value. Fibonacci's ratios approach approximately 1.618, a value mathematicians call the golden ratio. The sequence has led us to another irrational number, one surrounded by beauty, mathematics, and an extraordinary amount of myth. Build a rectangle whose long side times its short side, and something elegant happens. Remove the largest possible square, and the rectangle left behind has exactly the same proportions as before.
Repeated subdivision suggests a spiral whose scale grows by the golden ratio, a mathematically precise logarithmic curve.
Over time, a seductive story grew. Perhaps this portion secretly governed nature, art, architecture, even human beauty. But measure carefully, and many famous examples do not fit phi precisely, or lack evidence they were designed around it. The nautilus is beautiful, but its shell is not a perfect golden spiral. Nature owes mathematics no such obligation. Yet phi does have genuine connections to growth, especially when repeated placement must distribute structures efficiently around a center. A rotation of about 137.5 degrees, the golden angle, can distribute successive growth remarkably well. Because the angle avoids simple fractional turns, new positions resist repeatedly lining up with those already present. Strip away the mythology, and the mathematics remains remarkable. Fate repeatedly transforms into simple expressions involving itself.
The golden ratio describes a remarkable proportion. But another constant appears when mathematics asks something different. How does change accumulate?
Some quantities describe shape. Others describe something more restless, how systems grow, fade, cool, and change through time. Suppose a quantity grows by 100%. Apply that growth once, and 1 simply becomes 2.
Divide the same growth into smaller, more frequent steps, and the final result becomes larger.
Make those intervals smaller and smaller, approaching continuous compounding, and the result converges toward one particular number. E emerged when increasingly frequent compounding approached continuous change, becoming mathematics' natural exponential constant. When growth is proportional to what already exists, exponential mathematics can describe the increase, at least while conditions allow. Reverse the process, and the same mathematics describes exponential decay, a constant fraction disappearing over equal intervals. Even cooling can approach exponential behavior when the rate of heat loss depends on the temperature difference. Unexpectedly, E also appears throughout probability, wherever repeated independent events and limiting processes create exponential relationships. And E has a remarkable property. The exponential function e to the x is its own rate of change.
Growth, decay, cooling, probability. Different phenomena can share the same mathematical structure when their rates depend on what exists.
Change reveals patterns through time. But another kind of mathematics asks whether structure can survive a change in scale. From high above, a river basin reveals branches within branches, carrying water across an enormous landscape.
A tree solves a different problem, yet its trunk divides into limbs, branches, and ever smaller twigs. Lightning branches too, not because it copies trees, but because electrical breakdown creates its own branching paths.
Inside our lungs, repeated branching distributes air through a vast surface packed into limited space. Measure a coastline from far away, then measure again more closely, and something strange happens. Its length grows. Smaller rulers follow more detail. The measured length therefore depends partly on the scale at which we measure.
Mathematics takes this idea further. A fractal can repeat a construction again and again across smaller scales.
Change the scale, and familiar structure returns. In an ideal mathematical fractal, this process can continue indefinitely. Fractals can even possess dimensions between familiar integers, more complex than a line, yet not completely filling a plane. Nature cannot repeat forever. Eventually, branches become cells, coastlines become grains, and the apparent self-similarity breaks down. Different forces create these forms for different reasons. Mathematics gives us a language for comparing their structures across scale. Scale reveals one kind of hidden order. But nature contains another, patterns that survive not zooming, but transformation. We recognize symmetry instantly. One side echoes another, creating balance around an invisible line. Mathematically, symmetry begins with a transformation. Change something, yet preserve an essential property of the original. Some forms survive rotation. Turn them by particular angles, and their structure becomes indistinguishable from where it began.
Inside crystals, atoms can repeat in ordered arrangements, creating symmetries that extend through space.
This is symmetry's deeper meaning. Not simply beauty, but something remaining invariant while everything else is transformed. Physics asks the same question of nature's laws. What can we change without changing the laws themselves? If the laws do not depend on where an experiment occurs, that symmetry connects mathematically to conservation of momentum. If those laws remain unchanged through time, another profound connection appears: conservation of energy. And when physical laws remain unchanged under rotation, symmetry connects to conservation of angular momentum. Noether's theorem reveals the deeper bridge. Continuous symmetries of physical systems correspond to conserved quantities. And sometimes the laws remain symmetric, while the state of a system chooses one possibility, breaking that symmetry. Rotation leads mathematics somewhere stranger. Turn a number through 90 degrees, and the real line is no longer enough. On the real number line, one equation seems impossible. What number multiplied by itself could produce -1? The name imaginary is misleading. I is not a physical substance, but its mathematics describes very real phenomena. Mathematicians expanded the number system and defined a new quantity, I, whose square equals -1. Adding I transforms a one-dimensional number line into a two-dimensional complex plane, where numbers gain a new direction. Geometrically, multiplying by I performs a 90-degree rotation. Multiply by I again, and 1 becomes -1.
Euler's formula reveals something deeper. Imaginary exponentials describe rotation through the complex plane.
Follow one component of that rotation through time, and circular motion becomes the mathematics of a wave. Electrical engineers use complex numbers to alternating voltages and currents, turning oscillation and phase into manageable mathematics. Sound, radio, communications, and digital signals become easier to analyze when oscillations are represented with complex numbers. Quantum mechanics goes further. Its fundamental wave functions are complex valued, while measurable probabilities emerge from their amplitudes. Square any positive real number, and the result is positive. Square a -1, and it is positive again. Expanding numbers gave mathematics a new dimension. But every number system still shares one remarkable point: 0. 0 looks like nothing. Yet turning nothing into a number became one of mathematics' most powerful ideas. As a placeholder, 0 lets position carry meaning. 1 becomes 10, 100, then 1,000. On the number line, 0 marks an origin. Positive numbers on one side, negative numbers on the other. Now count upward. Whatever number you reach, adding 1 produces another. There can never be a largest whole number. We call this absence of a finite bound infinity. But infinity is not simply a very large ordinary number. Strangely, all counting numbers can pair 1 to 1 with only the even numbers, despite the evens seeming like half. Then Cantor discovered something even stranger. Some infinite sets are mathematically larger than others. Even between 0 and 1 lies an uncountable continuum of real numbers, more than counting alone can enumerate. Calculus often uses infinity through limits, describing what happens as a process continues without bound. 0 and infinity are not simple opposites, yet both appear whenever mathematics pushes toward boundaries, limits, and scale. They arose from different questions and different worlds, yet somehow, all 5 can meet in a single relationship. Across our journey, 5 ideas have kept returning: 0, 1, pi, I, and e. 5 ideas, born from different mathematical questions: change, rotation, circles, unity, and zero. That number is E, approximately 2.718, the natural constant of continuous exponential change. I expanded numbers into the complex plane, where multiplication could become rotation. Pi began with circles. Measured in radians, pi is also exactly half a complete rotation. Its beauty is not magic. It comes from deep connections between exponentials, rotation, trigonometry, and the complex plane. Euler's formula provides the bridge. An exponential involving I describes rotation through an angle theta. At that half-turn, the horizontal coordinate is -1, while the vertical coordinate is 0. So the expression collapses, e to the power I pi equals -1. Add 1 to both sides, and 5 fundamental mathematical ideas suddenly meet in a single identity. Now choose one special angle, pi radians, exactly half a turn around the circle. Change, rotation, circles, unity, nothing. Ideas encountered separately now reveal that mathematics contains unexpected bridges between them. But the equation exists in our mathematics. The ocean, the stars, and the universe existed long before we wrote it. The universe did not wait for us to describe it. Waves moved, planets turned, and stars burned before mathematics had names. What humans discovered first were patterns. Repetition, proportion, symmetry, growth, cycles, and structure. We gave those patterns symbols, names, definitions, and rules, and built the language we now call mathematics. And something remarkable happened. Equations did more than describe what we saw. They let us calculate what would happen next. Again and again, mathematical structures have predicted measurable behavior before experiments or observations confirmed the details. Perhaps mathematics is our invention, a language shaped precisely because we designed it to describe the patterns we encounter. Or perhaps we discover mathematics, relationships that were already true, waiting for minds capable of recognizing them. But an equation is not the phenomenon itself. Mathematics is a map, and reality remains the territory. Numbers, circles, growth, scale, symmetry, waves. The journey changed not the universe, but the way we learn to see it. From structures smaller than sight to systems larger than worlds, mathematics keeps giving us ways to uncover relationships. And one mystery remains. Why is mathematics so extraordinarily effective at describing a universe that never speaks in equations? Perhaps the deepest mystery is not that mathematics works, but that the universe gives us anything to understand at all.